Today there will be Alexei Shan. So our next speaker will be Jan Vybiral from Prague Technical University. And let me see the title again. And he's going to talk about robust and efficient identification of neural networks. So please, Jan, stage is yours.
So thank you very much for inviting me and for putting this meeting together. So I think this is indeed a great idea, and maybe I would suggest that we somehow continue in this possibility to visit the meetings online, even when we come back and see each other together, hopefully in a close future, because I think sharing these meetings online can allow some students and many other people to visit meetings, well, even to people who would otherwise have some troubles to travel around and pay for that and have the time for that. So I will try to share my screen. I hope you see it now. So is everything okay?
At least for me, it looks good.
Okay, so great. So I think now the time is also there, so I can start. So I will talk a bit about work which we did already some time ago and developed after that. I wasn't really sure which audience would come together, so I will start with even some general slides, but probably for most of you, this general stuff is not really needed. And then I will evolve the talk in the direction of structural assumptions on functions. And at the end of the day, I will come to the main topic, which is one or more layer neural networks. So the general task of sampling or approximation theory dealing with function values can be described like that. We have a function which has some properties, which are typically modeled by being in a unit ball of some function space, but can be actually also different. And then we choose sampling points x1 up to xn. It might happen that these points were actually chosen already before, so that we are not allowed to freely choose them, but that they were already selected before we came to the problem. And we have the function values, which might be noisy or which might be exact. And we would like to say something about the function, and which means that we try to produce a function g, which is close to f in some sense, typically in some norm. And the aspect which I would like to talk about is about how close the g can be to f in high dimensions. And there is decades, if not maybe 100 years of history about this task. And there is many results, many names. I try to collect some of them, but probably many others are still missing. And so please don't be angry if you don't find your name on the list. I'm very sorry for that. And the message is that if the dimension grows larger, then usually the decay of this error becomes much smaller. And typically, if the S stands for smoothness, which was a good assumption in the last 100 years, then unfortunately in the exponent of n, we have S over D. So if the D is large, the decay becomes very slow. The example which I like the most of this area, well, there is more theorems, but this one is really my favorite, and it comes from Erich Nowak and Henryk Woźniakowski from 2009, and it goes like that. So for your class, for your information about the f, about the functions which you would like to approximate, You take the class fd, which are functions on the unit cube, so 0, 1 to the power d. This is a nice set with measure 1, so the problems are like normalized. And they are C infinity, the functions. So you know actually quite a lot about the functions, namely that their all partial derivatives in the uniform norm are bounded by 1. So these are functions like sinus, cosine, and so on, which would all fulfill inequalities like that. But unfortunately, in this beautiful paper from 2009, they were able to show that the initial error, meaning the error which you do if you don't have any sampling points at all, so you just make a blind guess and that's it, that this initial error is the same as the error of uniform approximation until the n becomes exponentially large in D. So this means that no matter which algorithm you produce, seeing such a nice class of functions, you don't have much chances to really make effective algorithms here. So this is called curse of dimension and typically is connected with some exponential growth of needed resources like sampling points or maybe also some other like running times of your algorithms. So exponential dependence on D, and if the D, of course, becomes even moderate, this becomes very quickly essentially deadly or very difficult to handle. So therefore, there is a line of research which appeared maybe some 10 years ago, but well, there is of course some forerunners as well, which tries to avoid this. And essentially the smoothness assumption was replaced by some structural assumptions. Like we know that the function in RD is of some special type, of some special form, or has some very special properties. And we try to use them in the recovery algorithms, and we try to avoid this exponential dependence in D. So for example, in the paper of Ron Devor, Guargana Petrova, and Przemysław Wojtaszczyk from Constructive Approximations 2011, they considered the so-called active variables, meaning we have a function which might depend on many things, but we have an intuition that it actually does not depend on so many variables, but that there is only few which explain the behavior of f. So this, I think nowadays is a very reasonable assumption because we measure many things, we measure many parameters, and at the end of the day, we know it that we probably measure too much. So we actually somehow believe that the quantity of interest, which might be anything in production, in biology, or anywhere else, actually depends on a much smaller number of the parameters, but we don't know exactly which of them play a role. So I think this scheme is already a very, well, natural one. And also here, it turned out that the number of sampling points can be reduced very much, and especially the dependence on D becomes only logarithmical. So although the smoothness assumed on G or F is not very large, it's only Lipschitz functions, by the structural assumption, the D is not that deadly and it grows only logarithmically in D, the number of sampling points. So this was revisited in a couple of other papers later on with even some like overview paper of Simon Foucault last year. But I will not go into these details. So there is much more on this setting. Just for curiosity, let me mention that there is even other, well, there is actually many more, but let me mention at least one other setting of structural assumptions. This setting comes essentially from stochastics, where it goes under the name of SPAM, meaning sparse additive models. So the shortcut is SPAM. So it's a bit confusing if I say that I will talk about SPAM, but I mean this structural assumption on functions. And for example, if the parameter R0 is set to 1, then the function is assumed to be a sum of univariate functions, which, well, each of them depend on some xj. And the number of these variables used is assumed to be much smaller than d. So in some sense, this becomes a special case of active variables where we even know that the dependence on each of the variables is only separated in this way. If we choose this parameter R0 a bit larger, then actually there is also bivariate, or in general R-variate functions coming up here. So in this way, we allow even for a bit more generality and a bit more, well, flexibility in this setting. And again, we studied sampling algorithms, recovery possibilities, and so on and so on. What I would talk about most in my talk are so-called rich functions and their variants, combinations, and sums. So a rich function on its own is actually a very simple function. Namely, we have a univariate function and a vector. This function might be called a rich profile, and this A might be called a rich vector. And the function fx is then given like this expression, where this is a scalar product between a and x. So this is just the inner product of these two vectors. And these functions are multivariate, of course. So the x is still in Rd, but actually the problem reduces quite quickly to univariate because the function is constant along hyperplanes. So anytime this scalar product, this inner product is, say, 0, then we have g of 0 and the function is constant on this large hyperplane. We can even consider different generalizations and variants, like there wouldn't be only one inner product, there would be more of them, like some matrix A times X, meaning we take scalar products of the rows of A with the column vector X, and that gives us K inner products, and the G would be K variate function. These functions actually appeared already some time ago, and I think already from the beginning when they appeared, and you see it in the title of the last paper mentioned here, they were connected with neural networks. So I will come to this later on, but I think that is probably the most important source of problems and, well, difficulties is what happens with neural networks, how to analyze it and how to understand it. So in that time, actually, the question was a bit different. Namely, these rich functions are considered to be very simple. And the question was, can we approximate a general, say, continuous function by sums or compositions of such functions? So these were taught like building blocks. And the question was if we could maybe somehow combine them in such a way that they could approximate more complicated functions. So in my talk, I will consider the sort of simpler problem, namely how to recover the rich function on its own. So let us assume that we choose indeed the simple setting, k is equal to 1, fx is g of this inner product, and we might consider a to be normalized and g to be, say, smooth for the beginning. And of course, we have two things to do, or that's at least, I think, the most natural approach, namely to recover an approximation of A and to recover an approximation of G, and hope that this approximation of G evaluated at the inner product of X with this approximation of A would actually be a good approximation of this whole function f. So we have two things to find, and it's not really clear from the very beginning which of them to look for first. So should we try to somehow get some information about how the G might look like, and then after that recover A, or do we want to recover A first, and then when we have the A to get some information about the G? And well, there is a simple formula which is really straightforward, namely that if you take the gradient of f, and the f is given like that, then actually this is some number, namely g prime at this point times a. So if you are somehow able to recover the gradient of f, and this quantity is different from 0, you get a multiple of a, and you have your vector essentially there. So the trouble is, well, the g prime at 0, because I mean the most natural point to start with is x equal to 0, might be 0 or might be non-zero. And it turns out that that plays indeed a very big role, and depending on the value of g prime at 0, the problem can become quite easy or quite difficult. So the first paper, at least what I am aware about on this stuff, goes back to Albert Cohen, Ingrid Dobucci, Rondevor, Kerkicharian, and Picard. And the setting was like that. I will mention that only just to give you an impression how such a theorem might look like, because it indeed gets a bit technical. So you need to put together all the assumptions on your function. So it has this structure where there are some assumptions on G and some assumptions on A. So for example, A was considered to be Q sparse, meaning from the unit ball of LQ, and the coordinates of A were considered to be positive. So with these two restrictions, the final theorem then looked like that, namely that you can recover a function f hat such that this uniform error bound holds, and that is the number of sampling points. So just again, for the curiosity, how did this approach work? So this approach used the assumption that A is positive, meaning that if I sample at these points, so along the diagonal, then I recover the function values of G immediately. So actually the approach was based on recovering first the function G, and only then recovering the A by methods of compress sensing. So that explains a bit why it was necessary that A is positive, because only if A is positive, you know that this grid becomes here a grid for G as well. And second, this Q ball plays a role to be able to use the compress sensing tools. So the main message here is that G goes first and A goes only second. Well, this topic was reconsidered a couple of times in several papers. I have no time to go into details. So with Massimo and Karin, we considered the problem as well, but our approach was different. We first tried to recover the A and only then to recover the G. With my PhD student, my former PhD student, Anton Kolek in Berlin, we considered what happens on the cube. If the ridge function is not defined on the ball, but on the cube. With Sebastian Meyer and Tino, we considered even lower bounds, because we were somehow annoyed that we have to assume this and that. And the question was, is it really like necessary, or is it only the artifact of the method? And well, the message was that essentially our assumptions, which we used so far, are quite natural and important, because if you leave them out, that there is not much chance to get like better bounds. And actually the curse of dimension might happen even for such simple functions as the rich functions are. And there is a follow-up work on rich functions on cubes, and again showing some lower bounds and the curse of dimensionality in this setting. So how is it all that connected with neural networks? So the study of neural networks came already in like 43, and it was indeed based on study of like human brain or brain of an animal. And there were connections and there were the neurons, and the mathematical model, which was accessible in that time, was that a neuron gets some inputs and have some weights and combines these inputs with these weights. And then there is a function which, depending on this combination, shoots some answer out. So if you write it down, then essentially this is a rich function. So the approximation of rich functions, which I talked about, can be also and essentially equivalently thought about as approximation of one single neuron. So there is an inner product between the inputs and the weights, and then there is a function, sometimes called activation function, which then produces a real number. So for like, mathematicians, it's more natural to talk about rich functions. For people from biology or, well, data analysis, a neuron is nowadays the thing. So here it's actually the same story in mathematical symbols. So we have inputs and we have weights, and we take the inner product and we have some activation function, and this is the output then. So from these inputs, the single neuron, essentially one rich function, produces this output. So in the area of neural networks, this activation function is usually assumed to be somehow given or fixed. So people play a lot with the weights, but they do not tune so much these activation functions. So they are somehow considered to be given. So our approach, where the weights and the function are to be found and to be like identified, is sort of a bit more general. After you have one neuron, you can actually put more of them. Of course, the brain has a huge number of neurons. So the study of neural networks also oriented on what are the connections between them. And the usual model used now, but there is many of them, of course, is that we have layers. Each layer has a number of neurons, so essentially rich functions. And then from one layer, you get what was output of one layer becomes an input of the other one. And there you go a couple of times in these hidden layers, and you get some outputs at the end. So essentially, you only make this graph between a large number of layers and a large number of neurons in between, and that is what you get. So now, well, we started with this issue already some time ago, and the idea was that we first consider only like one layer of a network. So after the work on rich functions, meaning on a single neuron, was done, the next question was what happens with one layer? And what happens is the following. So we have these neurons, and there is some of, well, there is a bunch of them, and the output of each of them then gets combined in this way. So we assume that our function fx is essentially, in the, I would say, more simple language, a sum of rich functions. And well, there was an obvious observation already in the beginning, namely that we can think about that as a general rich function with, well, M here. So if the A would be the matrix with rows AJs, then this is a function of the type J of AX. But of course, we hoped, and that is indeed the case, that this special structure where we don't have a general m-variate function g, but we have m univariate functions g1 up to gm would of course play a big difference, would make a big difference. And that is indeed the case. So this, this last part of my talk is based on a paper with Massimo Fornazier and Ingrid Dobucci, which is now to appear soon in Information and Inference journal. So again, as before, we would like to identify first the vectors, the a1 up to am, and then the functions g1 up to gm, and hope that the same structure built up from these approximations would, at the end of the day, approximate the function f as well. So, well, the paper has a number of different steps and different like algorithms which hope to achieve the individual tasks like one after another. So first, we make an observation that if we take the gradient of f, then we have this formula. So we have a linear combination of these unknown vectors. We don't get a single one of them at the spot, but we have a combination of them. So if we sample this gradient at different points, we get different linear combinations of AJs. And if we sample on a number of, say, randomly chosen points, then at the end of the day, we should get elements of this span of A1 up to AM. And if the number of sampling points was not too small, then we actually get a stable approximation of the subspace. So that is the first point. And so we get some subspace A tilde, and without going to the details, this subspace can be used to reduce the dimensionality. So our aim first was that M is much smaller than the dimension D, that we have really a problem which sits in a huge dimension. And with this trick, we can already reduce it to M-dimensional problem. So this, say, simple substitution essentially reduces the dimensionality from D to M. But what do we do then? So we have now essentially recovered the right subspace, and we have an m-dimensional problem, but we still have only the subspace. We don't have the AIs, the individual AIs. We only have their span. So we go for second order derivatives. So if you are new to this area, you might think that this becomes very nasty numerically.
Там конференція одна, то я хочу послухати.
Sorry?
Excuse me, is there a question? Probably not. Well, please continue.
Okay. So actually a similar topic was considered by the guys from machine learning community some years ago, and they actually found it necessary to go even to third order tensors to recover the structure of the network. So from this point of view, our use of only second order derivatives is actually a big step forward and makes the things more feasible. So what do we do with second order matrices? Well, if we sample the gradient, the second gradient, this, Hessian matrices, at some point, we get a linear combination of rank 1 matrices.
Jan, sorry, may I interrupt you just for a second?
Yes.
Could you please mute your microphones if you enter the Zoom room here? Otherwise, there is too much noise and the talk is not really understandable. Thank you. Okay.
Okay, so yeah, so in this way, essentially a similar way as before, we get the span of these rank 1 matrices. So the A, so this, calligraphic A is the span of rank 1 matrices. We don't get it exactly. We get, again, only some approximation of A tilde. And well, we would like to find these AIs in this subspace. And what did we propose is the following. So these matrices are rank 1 matrices, which are in the A, in this, calligraphic A. So if we would have access to this A and would be able to find rank 1 matrices in this subspace, then we should land up at AI or minus AI. And we would be happy because that's exactly what we want to get, what we want to approximate. So because we have only this A tilde, there wouldn't be any rank 1 matrices in general in this subspace. So we look for matrices where actually the operator norm is as close as it goes to the Frobenius norm in this subspace. So we propose this non-convex problem, which is written like here. In our subspace, which we indeed have, we try to find for matrices which have the largest operator norm, and well, which you can interpret also as that the operator norm is as close as it goes to the Frobenius norm. Of course, we were like disturbed by why should we use non-convex optimization, which is, well, really painful numerically and analytically. But actually this algorithm, any algorithm which tries to recover the AJs can also land up at a different AJ. So there must be a possibility that this algorithm lands up in any of these. So most likely it should be non-convex because it should have more minimizers or solutions. So that's why we had to accept this non-convexity of this optimization problem and go with that. So I will not give many details here. There was a pretty long analysis of this optimization problem, and we've shown some first and second order conditions about the the maximizers of this optimization problem. And in the end of the day, we could come up with a theorem that indeed this algorithm lands up in an approximation of these neuron vectors A1 up to AM. So this is indeed like, well, maybe 20 papers of 20 pages of a paper. And it's only here to give you some idea how it all looks like. There is even more technicalities somehow. So all that works only if the AIs are nearly orthonormal. And if they are not, then we apply a technique which in data analysis is called whitening. But of course, we had to think about that this whitening is also like that we can really combine it with our sampling scheme, that we really work with objects which we have already at hand. There is actually a version for what we call passive sampling, namely that the points were already pre-selected before we came with our algorithm. We only need to assume that they were pre-selected at random from a distribution with known density. And after all that and some other well, tools and techniques were used, the identification of GIs is already quite easy because we have approximation of AJ, we take the dual basis and we sample along the dual basis, and that's it. And these G heads would be approximations of this G. So I will not give like a main theorem of all that because it would have to combine all what I've said so far in this last part. It's essentially really a pipeline of algorithms which are performed one after another. I will give you on my essentially last slide a picture on the numerics of this problem. So here we have, so we assume that some neural network or the sum of rich functions was given and that we would like to recover it. So if we use the approach, which is like usual in learning a neural network from given data, then we'll end up with the red line, and you see that it actually goes down very quickly because it's very, very effective. But that at some point, with the number of sampling points growing, our method, which is the blue one, so it performs badly in the beginning, but it actually starts to improve until it recovers the structure of the network very well, and it beats the usual approach. And it's even like better, this difference, if you approximate the neural network, not in the L2 sense, but in the L infinity sense, where the usual approach still has some points where the error is large, where actually by approximating the structure of the network, we are essentially able to cover all the points completely. So maybe the last fact I would like to mention is the following. The interest in recovering the neural networks, not only to fitting the outputs, but to understand its structure is becoming more and more important, with neural networks being used in areas where we really want to have worst case guarantees. Like if your neural network is used in some automatic car, you really want to be sure that no matter what happens on the street, you are safe in the car, not only on the average, but essentially in the worst case. So with neural networks being used in security, in some really important parts of our life, we are more and more interested in understanding the structure and indeed on going into the details and really understanding the structure of it. So I thank you for your attention, and I would be very glad to get any comments and questions of yours.
So thank you very much, Jan, for your interesting talk. There is already Mario waving his hand, so please ask a question.
It was basically clapping for the end of the talk, but yes, also take it as a raised hand. It's fine for me. So Jan, thanks for the interesting talk. May I ask you something on the side? You said that rich functions basically are the functions you should consider for neural networks, right? But in the very beginning, you already used that all the data you get is somehow combined by just taking an average, right? Which is very linear. And so is there a reason for doing that, or is it still not clear that this is a good idea, right? So because you tackled the activation functions and how to use other activation functions, but you haven't tackled the point that the data is basically brought together just by an inner product.
So the whole idea of neural networks, I think, well, essentially one should be able to find some like philosophical or historical lecture on that, and I'm not the expert, so probably online you find much more sources than what I can give to you. But essentially, as I get the history, then there was an interest in neural networks because of the biological reason in the 40s. And at some point, this line of research was essentially abandoned because the computers in, say, 80s, they were not able to handle all that. So neural networks are probably not very effective when it comes to using your data. So essentially, you need a lot of data points. And second, they are numerically pretty difficult to train. So there is the non-local optimization in training the weights. And in 80s, this was indeed a problem. Only much later, we realized that through internet, we have a lot of data because people upload some pictures and so on. So you can share your databases. and that the computer power increased. And people realized that this concept is actually useful, and there was a wave of papers about that neural networks are superior to human powers in this or that area. But as far as I know, essentially, they are used because they are successful. So it's actually possible that there is another concept, some like modification of this neural network concept, which would turn out to be even more successful. So there is not so much theoretical analysis like that. The best what you can do is to throw a neural network. It just only, well, it worked for so many people. So of course, some other people try as well. So in the best case, I think our analysis of neural networks, and by that I mean not like only our, but like of the whole, mathematical community, could come up with a bit different scheme or model, which would ensure maybe the same or even better performance by choosing a bit different setting from the very beginning. And I think that would be really great, because we as mathematicians and theoretical guys could show ourselves important and useful, because we could really improve some electro-engineering ways how to deal with data.
Okay, thanks. So since we have quite some time, I guess, let me ask the second question. So there's just that's only a historical reason you say that that we think a neuron is based on some maybe complicated function applied to an inner product. That there is no numerical reason, or you haven't checked if you can do it better or something. It's just that is how everyone is doing it, right? Or
well, I mean, there is a bit of background. Like, we know that
Sure.
the real neurons, that they get some signals by that synapses which they have, and that at one point they fire again, or this like dies out and the neuron stays essentially inactive. So of course we know nowadays a lot of the brain. But I think essentially these two lines of research essentially separated. So essentially there is, ways how to tune your artificial neurons and neural networks without really making biological considerations, if like 100 layers is more natural and corresponds more to the brain than 300 or 500 layers. It's just essentially experience, different like models and different testing, and seeing what works the best for you.
Okay, thanks, Mario, for initiating the discussion. I have a question, Jan.
Yes.
Could you comment on this fundamental difference of approximating sums of rich functions by something and approximating functions by sums of rich functions? Because I mean, in some decades ago, there have already been a lot of results in that.
I mean, the difference is quite well natural and important. So in the work before, the neural networks were considered to be a composition of rich functions in some way. And of course, there was a question if you can approximate all, say, continuous functions in this way. So there is a lot of theorems which we know from analysis, like every L2 function can be approximated by sum of trigonometric polynomials, and so on and so on. So there is a bunch of theorems which go back to maybe 19th century of Bernstein polynomials and so on, that every continuous function can be somehow approximated by something. So this line of research was to show that indeed every continuous function, or maybe some other assumptions as well, can be approximated by some mixture of rich functions. By the theory, these were of course very important like results, But for what we do, the question is a bit different. Namely, you now consider even the rich functions as objects of interest on their own, and you study how well can you identify them by some sampling, for example, or by any other information. So we now essentially don't aim so that we would claim that you can mix up everything or cook up everything from rich functions. We essentially go only to this. Now we have a few of rich functions. Are we able to really see their structure? So it's essentially a completely different problem.
Yeah, thank you for this comment. I just asked because there was recently, I attended a survey talk by Ron DeVore. Maybe you have seen that. It's on that first part of the question. There were some surprising results how to approximate given functions by rich functions. So, but as you said, this is not your topic, so you consider the other question here. So I think Kostya has a question.
Yes,
Yeah.
Jan, thank you for a wonderful talk. Do you hear me?
I can hear you, yes.
Okay, okay. So I have some technical questions. Actually, we are working at a rather similar problem at this time, and I will talk about it later in this week. And your algorithm, it works with approximate values, measurements, or are they without noise?
Well, the paper, the last one, is pretty long. It has like 70 pages, and there is different aspects. So one of them was also noisy measurements. So our first approach was to use exact information, but of course the question of noisy measurements appeared as well. So it's to some extent discussed also in the paper.
And your algorithm is deterministic, or there are some random parts of the construction?
There are some random parts. So for example, when we choose where to sample the gradient, then we say that we throw a few points at random and we sample at random. So there are some steps which are essentially randomized, but probably it wouldn't be that difficult to somehow de-randomize them as well. Not considered, but the use of randomness which we had wasn't really like very sophisticated or something which probably couldn't be that like de-randomized.
And the functions are assumed to be how smooth?
The smoothness is essentially limited by the algorithm. So we sample the second order Hessians. So we need the second order derivatives to be a bit smooth. So the smoothness is like constant, and say 3 times differentiable is enough for all dimensions. I had no time to talk about that, but actually there was a work of Pincus, and I think the second guy was Buhmann, who considered sum of rich functions as well. But when the sum had m terms, they had to consider m derivatives, which of course is numerically really a big problem. So our like motivation was we want to keep the number of derivatives used like tractable or doable or well, implementable, so that we go only for second order derivatives was also motivated by the previous work, which analytically works very well. But there were also heavy considerations about if it works numerically as well, because of these very high order derivatives used.
Thank you, Kostya, for the question. And as Kostya mentioned, he's going to give a talk on Friday on a similar topic. Recovery of rich functions with Yuri Malikin, right? It's Friday. Yeah, it's Friday.
Thank you.
Okay, are there further questions? If not, on there? No. If not, then I would suggest to do a small break of 10 minutes. Of course, you may discuss here on your own, and then 10:45 will be the next talk by Katarina Bojarska from Kiev.
Whatever, right? But now you have this optimal